we'll starting part 3. We'll start talking about metabolism, which is, we're still in the pharmacokinetics. Metabolism is the biotransformation of the drug into a water-soluble, more readily excreted form, or into a form that can be more readily used by the body. The liver is the main organ that performs the body's metabolic function. It has a high concentration of metabolic enzymes. And that, remember when we were talking about the first pass, that is why the first pass is significant to the bioavailability of a drug, particularly the drugs that, or mainly the drugs that are administered orally. The kidneys, the intestines, the GI tract, the lungs, and the skin also can serve as mechanisms for metabolism. The kidneys and the intestines particularly, and there are actually some circulating enzymes that circulate through the body that contribute to metabolism. Drugs can be metabolized from active components into inactive or less active ones, meaning they are metabolized into the active components, and then as they're used by the body, then they become inactive or less and less active. But drugs can also be biologically transformed from an inactive parent drug into an active metabolite. And drugs that are transformed from this inactive parent state to an active metabolite are called prodrugs. And it's a prodrug because it is a precursor to the active drugs. The synthetic opioids like oxycodone or OxyContin are examples of this. They are changed from their original form, which is pretty inert or inactive, into a form of codeine. So those are particularly examples of prodrugs. Not all drugs are metabolized to the same extent or by the same means. Drugs are usually metabolized in 2 phases. Once they get to the liver, enzymatic processes of oxidation and reduction that changes the drug to a more polar or water-soluble compound. And then in phase 2, usually it adds something. It adds a conjugate or an assistant or an enzyme that will further help break it down and increase its water solubility. This, again, this increased water solubility enhances excretion. It also enhances the ability for the drug to get to where it is needed to act. Now we come to one of the more difficult concepts to understand when we're talking about drug metabolism. The cytochrome P450 system is a group of enzymes that are present in the liver that are responsible for the metabolism of a lot of drugs. They're really composed of superfamilies, and they estimate that there's more than 100 of these CYP450 enzymes, but there's only about 15 total that actually are important contributors to drug metabolism. Now, their common feature is their lipid solubility. Most lipophilic drugs, which we said lipophilic are those that will dissolve in fat or protein, they need to be converted to water-soluble form in order for them to be excreted from the body. Also, these CYP40 enzymes do that, but they also metabolize and convert the drug to its usable form so that it can be used where it is needed. Now, these, I said, the CYP450, they're a large family. And many of the drugs are similar. They look like cousins or like they're in the same family with their composition. So the thing that becomes problematic is that they are similar, but they're different, but yet they compete with one another for the availability of the CYP, the different CYP 450 enzymes. So this can be when you're having two drugs given together that are similar and are metabolized similarly by the CYP 450, then that's where we get into our drug-drug interactions. There are some drugs that become inducers, so there are some of the CYP 450 that enzymes that some of the drugs actually induce or stimulate the production of the CYP 450 enzymes. This will increase the amount of enzyme available in the liver to metabolize the drugs. So therefore, it will decrease the amount of drug that is circulating throughout the body. So if a drug stimulates or induces CYP to be more to be made, then this drug is metabolized more quickly, and then the amount of free drug is there's less of it circulating in the body. And then some drugs are inhibitors. They decrease the production of the CYP enzyme, and therefore metabolism is decreased, so that increases the circulating level of the blood. Now, these are something that you need to kind of understand, that this cytochrome P450 substrates are oftentimes what are responsible for our drug-drug interactions. So when inducers and inhibitors are competing for similar cytochrome P450 enzymes, you can see how this could be problematic. Whichever one wins, let's say the drug is an inhibitor, so it's kind of stronger and it wins the battle between inducing or stimulating CYP 450 or decreasing CYP 450, then if it's inhibiting, then you are not going to have enough of the CYP 450 enzyme to break down the other medication. So you're going to get a buildup of the other medication because you are going to have more free drug circulating in the body than that drug was designed for. So you can see how this competition between inducers and inhibitors through that CYP 450 system is going to be problematic. Now, I had to have the advantage of having had an advanced pharmacology course fairly recently, and I have an app on my phone that tells me whether this is a drug that is a strong CYP 450 inhibitor or inducer. You will not need that for your pharmacology here, but I just wanted to make you aware that this is the cause of drug-drug interactions. Other factors that influence the rate of medication metabolism are age, increased medication metabolizing enzymes, which is what we just talked about, that first pass effect. The two medications are metabolized along the same pathway. Again, that's pretty much what we were just talking about. And the nutritional or health status of the person. When we go back to age, infants have a very limited medication metabolizing capacity, and also the aging process influences medication metabolism. As we age, the enzymes decrease in the liver, our circulation is not as good, and there are different things that are related to aging that will affect the way the body metabolizes medications. Also, kidney function and liver function are huge factors you must think about. An increase in certain medication metabolizing enzymes. This is because this causes a medication to be metabolized sooner, requiring an increased dose to maintain a therapeutic level. Ethnic or genetic differences also occur, and research has shown that some patients are supersynthesizers of, let's say, opioids, and this is true. This is some evidence-based information that they have found, that, some people call for pain medication, like you give it to them, and 2 hours later, my pain is back. And then other people go 6 to 8 hours and they're really drowsy, and it seems to be that the pain medication is really affecting them. And so you look at the person who, after 2 hours, and I'm hurting again. But scientifically, they have found that they are super synthesizers of opioids, that these people have that CYP450 enzymes and that are inducers, and they quickly metabolize it. So you need to increase dose to maintain therapeutic levels. Now, with opioids, of course, we're going to be very careful. We're not going to give somebody an opioid every 2 hours. But for that person, instead of giving, if they have an order for 1 to 2 tablets, we're going to give them 2 as opposed to 1. Again, there's also ethnic and genetic differences that we're going to talk about a little bit later related to metabolism. It has been found that certain Asians, certain groups of Asians will metabolize Coumadin differently, and you have to adjust their Coumadin or their blood thinner, that's an anticoagulant. You have to adjust their doses differently. Most drug testing research was done on white males. So when new drugs were introduced and the research that was initially done on white males, they began to see that different ethnic groups reacted differently, women reacted differently. So research is now changing, and they have a different view. So they're not just all white males. I hope they were learning that. Again, the first pass effect we talked about with oral medications, that first pass effect, enzymes in the liver may inactivate to some extent that medication. Again, some of this is due to the CYP450. But there are some medications that the first pass effect causes it to be completely inactive. Nitroglycerin is an example. Nitroglycerin has to be dissolved under the tongue, so it's absorbed directly into the bloodstream. Because if you swallow it, first the stomach acids begin to make it inactive, and then if any of it makes it to the liver, it becomes completely inactive. So that's an example of how the first pass effect can really wipe out any of the therapeutic effects that you want. Similar metabolic pathways, as we talked about with the CYP enzyme, they can interfere with one another with the metabolism of one or both medicine. If it's whichever one wins out, the inducer or the inhibitor. We talked about if the inhibitor wins out, then you've got too much of the other medication circulating, and you can get to toxic levels. But if the inducer wins out, then the medication that is an inhibitor, you're going to have subtherapeutic levels. You're not going to have enough of it circulating. And with nutrition and health status, a malnourished client may be deficient in the factors that are necessary to produce specific medication metabolizing enzymes. If you remember that you need protein, which breaks down to amino acids. Amino acids are the building block. Also, you need albumin because that's part of a protein. You need those, and you have to have those in order to build adequate enzymes. So if you're undernourished, then you may not have the appropriate enzymes that will break down or metabolize drugs. Obesity, we've discussed that a little bit. With obesity, as discussed with distribution, the fat cells, since a lot of these are lipophilic, they will go to the fat cells and just kind of store there. Also, fat cells contain hormone particularly estrogen, which